A chip smaller than the palm of your hand just solved a problem in under 5 minutes that would take the fastest supercomputer on Earth 10 septillion years to finish. That is not a typo, and it is not marketing exaggeration dressed up for a headline. It is a real number published by real physicists, and it is so large that it stops making intuitive sense. Even stranger, the man who leads the team that built this chip stood up afterward and said something almost no serious scientist at a major tech company has ever said in public. He said the only way to explain what just happened is that the computation did not happen inside our universe alone. Today, we are going to walk through exactly what this chip did, why the numbers involved break normal human intuition, what Google's own lead scientist actually claims about parallel universes, why plenty of physicists think the claim goes too far, and what has happened with this technology in the time since. Because the story did not stop, where most coverage of it ended. In December of 2024, Google's quantum AI division unveiled a new quantum processor called Willow. The headline number everyone repeated was the speed comparison, 5 minutes versus 10 septillion years. But speed alone is not really the interesting part of the story. The interesting part is scale. 10 septillion is not just a big number the way a national debt or a distant star's mass is a big number. It is a number so far beyond anything in ordinary experience that it stops being meaningful in the normal sense. Even if every computer ever built by humanity had been running non-stop since the beginning of the universe, none of them would have finished this particular calculation. Willow finished it in under 5 minutes. Earlier quantum chips, including Google's own previous processor called Sycamore, had already hinted at this kind of gap back in 2019, but there was always room for doubt, always a chance that classical computers running smarter algorithms could eventually catch up and close the distance. In the years right after that earlier announcement, some researchers did in fact find improved classical methods that narrowed the gap considerably, which is exactly why skepticism persisted for so long. Willow's results, several generations of hardware later, made that same kind of catch-up look far less plausible, since the gap this time was not measured in an improved percentage, but in an entirely different order of magnitude. This no longer looks like two technologies racing each other along the same track. It looks like two fundamentally different categories of computation. To understand why, you need to understand what actually separates a classical computer from a quantum one. A regular computer, no matter how fast, works through information one step at a time, tracing a single path from question to answer, the same way a person might work through a long division problem one line at a time, no matter how quickly their pencil moves. A quantum computer does not work that way at all. Instead of bits that are strictly either a 0 or a 1, it uses qubits, and a qubit can exist in a mix of both states at once, a property called superposition. On its own, that already lets a quantum system represent many possibilities simultaneously, rather than one at a time. But the real power shows up once qubits become entangled with each other, linked in a way where the state of one instantly affects the state of another, no matter how the system is arranged. When that happens, the number of possible states the system can represent does not just double or triple. It explodes exponentially. By the time you reach roughly 100 qubits, which is right around where Willow sits with its 105 qubits, the number of distinct states the system can represent is larger than the total number of atoms in the observable universe. Sit with that for a second. A machine that fits on a lab bench, cooled to a temperature colder than deep space, is working with a number of possible configurations that exceeds the number of atoms in everything we can see, everywhere, across the entire cosmos. That fact alone raises an uncomfortable question. A classical computer does its work using the physical hardware sitting right in front of you, transistors flipping on and off inside a chip you could hold. Every bit of that work happening in a location you could point to with your finger. If a quantum computer is genuinely juggling more possible states than there are atoms available anywhere in the observable universe to represent them, then where physically is all of that work actually happening? It cannot simply be happening inside the chip itself, since the chip is made of a finite, countable number of atoms, and that number falls dramatically short of what the calculation apparently requires. That question is exactly where physics stops being purely a hardware conversation and starts brushing up against philosophy. And it is not a question that engineers trained purely in circuit design are typically equipped to answer on their own. For decades, there's been a serious, if controversial, idea sitting inside quantum theory called the many worlds interpretation, first proposed by physicist Hugh Everett in the 1950s, and later expanded on by people like David Deutsch. The idea is that every quantum event does not simply produce one outcome. It produces every possible outcome, each one playing out in its own separate branch of reality. Most people encounter this idea through science fiction, time travel movies, or comic book multiverses, but a meaningful number of serious physicists, including some who have spent their careers on the foundations of quantum computing, take it seriously as a genuine physical explanation rather than just a fun thought experiment. It is one of several competing interpretations of quantum mechanics that all make the exact same experimental predictions while disagreeing sharply about what is actually happening underneath those predictions, which is part of why the debate has never been fully settled by evidence alone. Under the many worlds interpretation specifically, a quantum computer's advantage would not come from doing everything inside one single reality. It would come from effectively spreading the workload of a computation across an enormous number of parallel branches simultaneously, then somehow combining the results back into one final answer that shows up on your screen. Google's own quantum AI founder, Hartmut Neven, leaned directly into this explanation in the blog post announcing Willow. He wrote that the chip's performance on this benchmark was so extraordinary that it had, in his words, borrowed the computation from parallel universes, and that this result lends real credence to the idea that we live inside a broader multiverse, an idea he explicitly credited to Deutsch's earlier theoretical work. That is a genuinely bold claim for the head of a major tech company's quantum research division to put his name on publicly, and it did not go unchallenged. Plenty of physicists and science journalists pushed back almost immediately. Critics pointed out that the specific benchmark Willow used, something called random circuit sampling, is a task engineered specifically to be difficult for classical computers and easy for quantum ones. Essentially, a test built to showcase quantum advantage rather than a broadly useful real-world calculation with practical output. Because Google itself designed and controls this benchmark, some scientists have argued it is not the strongest possible evidence for something as enormous as proving the existence of parallel universes, and that simpler explanations, rooted entirely within standard quantum mechanics, without needing to invoke separate universes at all, can account for the same result. Some commentators have also noted that Google, as a company facing intense competitive pressure in other areas of technology, has an obvious incentive to frame its results in the most attention-grabbing way possible, which does not make the underlying science wrong, but is worth keeping in mind when evaluating just how far to take the framing. In other words, this remains a genuinely contested interpretation within physics, not something settled science has confirmed. What almost everyone agrees on is that the raw computational result is real and enormously impressive, independently verified through peer review and published in the journal Nature. What remains fiercely debated is what that result actually implies about the deeper structure of reality, and reasonable, well-credentialed physicists land on very different sides of that particular question. Whichever interpretation eventually wins out, quantum computers do rely on something that is genuinely strange even under the most conservative reading of quantum mechanics, a phenomenon called interference. Different possible quantum states inside the system interact with each other as the calculation runs, reinforcing the states that lead toward correct answers and effectively canceling out the ones that lead toward wrong ones, in a process that has no real analogy in the world of classical computing at all. That interference is, in a very real sense, how the machine ends up landing on the right answer at all, rather than just noise. And engineering a quantum algorithm, well, essentially means designing it so that wrong answers cancel each other out as thoroughly as possible, while the correct answer gets reinforced again and again through the run of the calculation. Under the many worlds framework, that interference gets interpreted as a kind of very limited overlap between separate branches of reality, not communication in any conventional sense, and certainly nothing like sending a message back and forth, but some deeper form of shared computation bleeding across those branches, just enough to influence a final outcome. Willow does not prove that. It does not open some kind of portal, and nobody involved in the research is claiming it sends or receives a message from anywhere else, nor that anyone could ever step through into one of these other branches, even if they do exist, but it does place a genuinely unresolved question about the foundations of physics directly in front of a working piece of hardware you can hold in your hand, rather than leaving it purely as an abstract debate confined to journals and conference rooms full of theorists arguing points that, until recently, had no obvious way of connecting back to anything you could actually build and test on a lab bench. Arguably, the more concrete and less speculative achievement buried inside the Willow announcement had nothing to do with parallel universes at all, and it may end up mattering far more in practice. It has to do with errors. Quantum computers are notoriously fragile machines. A tiny vibration, a trace of stray heat, even a faint electromagnetic signal nearby can disturb qubits enough to corrupt an entire calculation, a problem researchers call decoherence. For roughly 30 years, this fragility has been the single biggest obstacle standing between quantum computers, as fascinating laboratory curiosities, and quantum computers as genuinely useful machines people could actually rely on. Normally, adding more qubits to a system makes this problem worse, not better, since more qubits generally means more opportunities for something to go wrong, like trying to build a taller and taller tower out of glass in the middle of an earthquake. Willow demonstrated the opposite behavior. As Google's team scaled the chip up, adding more physical qubits arranged into what are called logical qubits, the overall error rate went down rather than up, dropping by roughly a factor of 2 each time they doubled the encoding, moving from a grid of 3 by 3 encoded qubits up through 5 by 5 and 7 by 7. A genuinely exponential improvement rather than the usual struggle just to hold error rates steady. That result, published in the journal Nature, is what quantum researchers call crossing below the error correction threshold, a milestone the field had been chasing since roughly the 1990s. Team members have described the moment the data came in as something close to a collective sigh of relief across the entire quantum research community, since it finally showed, on real physical hardware rather than purely in theory, that the whole underlying strategy of quantum error correction actually works the way decades of mathematics had predicted it should. It matters because it suggests, for the first time with real hardware evidence rather than pure theory, that quantum computing might actually be able to scale up towards something genuinely practical, rather than staying permanently stuck as an impressive but fundamentally limited lab demonstration. Chemistry simulations that could speed up drug discovery, new battery and material designs, more accurate climate modeling, and entirely new approaches to artificial intelligence have all been floated as areas that a truly scaled-up, error-corrected quantum computer could eventually transform, though none of that has actually arrived yet. And turning this specific error correction milestone into any of those real-world applications will likely still take years of additional engineering work. The story did not end with the original December 2024 announcement. And this is where a lot of casual coverage of Willow stopped paying attention, even though the actual research kept moving. Through 2025 and into 2026, Google continued building on the same underlying chip architecture, and in April of 2026, the company announced what it called the first ever demonstration of verifiable quantum advantage using Willow hardware. A milestone framed as a critical step toward genuinely useful quantum computation, rather than just an impressive but narrow benchmark result. The distinction matters to researchers in the field, since a raw speed benchmark like random circuit sampling is one thing, but a result that can be independently checked and verified by outside parties, confirming the quantum system actually did what it claimed to do, is a meaningfully higher bar to clear. Around the same period, Google expanded access to the Willow platform, opening it up to outside research partners through an early access program, extending access to researchers in the United Kingdom through a national quantum computing center. Moves clearly aimed at getting more of the scientific community actually running experiments on the hardware rather than simply reading about it secondhand. The company also began diversifying its hardware approach, announcing in March of 2026 that it was adding a second different kind of quantum hardware built on neutral atoms alongside its existing superconducting qubit approach, essentially hedging its bets on which underlying physical technology will scale most successfully toward truly large fault-tolerant machines, since nobody in the field is entirely certain yet which physical platform will ultimately win out. Google has laid out a 6-stage roadmap toward that goal, and Willow itself represents only the second milestone on that roadmap. Roughly 100 qubits, with early-stage error correction working the way theory predicted it should. The next milestones on that same roadmap involve demonstrating a long-lived logical qubit that can hold its state reliably over much longer stretches of time. And eventually, a working logical gate operating between 2 separate logical qubits, both necessary building blocks on the road toward a genuinely fault-tolerant large-scale quantum computer capable of running the kind of complex extended calculations that would actually matter for drug discovery or materials science rather than a single narrow benchmark. As of the middle of 2026, Google has not yet published a peer-reviewed demonstration of either of those next 2 milestones, so the field is still watching closely to see how quickly the next step actually arrives. And Google itself has been notably careful not to attach a firm public timeline to when those milestones might land. Google is also no longer working in the space alone at the top tier. Competitors have been racing to keep pace, and 2026 has turned into a genuinely crowded field rather than a solo Google project running unopposed. IBM has been pushing its own processors, including a newer 120-qubit chip called Nighthawk, aimed at reaching practical quantum advantage on real-world problems by the end of 2026, and multiple other national research programs across countries, including China, Canada, Germany, and Japan, continue investing heavily in their own quantum hardware efforts, each pursuing a slightly different underlying physical approach to building qubits, from trapped ions to photonic systems built entirely around particles of light, rather than superconducting circuits cooled to near absolute zero. Private investment has followed a similar trajectory, with venture funding into quantum computing startups climbing sharply through 2025 and into 2026, as investors who had previously treated the entire field as a distant speculative bet started treating it as a genuine near-term technology race worth putting real capital behind. None of these competing efforts have yet matched Willow's specific below-threshold error correction result on published peer-reviewed hardware. But the overall race has clearly accelerated rather than settled down since Willow's original debut. And with new funding, new academic partnerships, and new government programs launching across multiple countries throughout 2025 and 2026, most serious security researchers tracking this space still place the point where quantum computers become powerful enough to threaten today's standard encryption methods, sometimes nicknamed Q-Day, somewhere out toward the early 2030s rather than tomorrow. Meaning Willow and its rivals represent genuine, measurable progress rather than an overnight arrival of world-altering machines. That distinction matters because it is very easy for coverage of this technology to slide from real, impressive scientific progress into breathless claims that outrun what has actually been demonstrated. And separating the two requires paying attention to exactly which specific milestone has been peer-reviewed and confirmed, versus which one is still sitting on a roadmap slide as an aspiration for some future year. Even with that caution firmly in place, it is worth sitting with just how strange the underlying physics genuinely is. Because you do not need to accept the multiverse explanation to find the story unsettling in a good way. A classical computer is fundamentally a machine of certainty. It takes a defined input, follows a defined set of steps, and produces a defined output every single time. In a way you could, in principle, trace by hand if you had enough patience and enough paper. A quantum computer is built on top of genuine uncertainty at the deepest level physics currently understands. And rather than trying to eliminate that uncertainty the way engineers usually try to eliminate noise and unpredictability from a system, it deliberately exploits it as the core resource that makes the whole machine work in the first place. Humanity has been here before, in a different form. People used fire long before anyone understood the chemistry of combustion happening inside it. Electricity was harnessed and put to use in wires and motors well before anyone had a complete theory explaining exactly what was happening at the level of individual electrons moving through a conductor. In each case, practical use arrived well ahead of full theoretical understanding. And society adapted to the technology long before the textbooks caught up with a clean explanation of why it actually worked. Quantum computing may be following that same pattern once again, except this time, the underlying phenomenon being harnessed is something as fundamental and strange as superposition, entanglement, and interference. Properties of reality that some serious physicists genuinely believe may only make complete sense if our observable universe is not the only one that exists. Willow does not prove the multiverse is real, and it would be inaccurate and misleading to claim otherwise as settled fact, no matter how compelling the framing sounds in a headline. What it does do is take an idea that spent decades sitting almost entirely inside theoretical physics papers and thought experiments, argued over in university seminar rooms and academic journals most people will never read, and force it into a very concrete, very public conversation involving an actual working device that sits on a lab bench, cooled down to temperatures colder than deep space, built by engineers, and capable of producing results that a growing number of serious scientists genuinely struggle to explain using conventional single-universe physics alone. Throughout history, humanity has kept expanding its understanding of reality by building better instruments rather than by pure thought alone. The telescope showed us that Earth was not the center of everything, dethroning centuries of assumption almost overnight once Galileo actually pointed a lens at the sky. The microscope revealed entire hidden worlds inside a single drop of water, worlds nobody had any reason to suspect existed until someone actually built a tool capable of showing them. Particle accelerators showed us that solid matter is, at bottom, mostly empty space animated by invisible forces holding it together. Quantum computers like Willow may be pointing towards something equally disruptive to our intuitions, the possibility that reality itself may not be a single unfolding timeline, but something closer to an enormous branching structure with our current moment representing just one thread inside something vastly larger than anything we have previously had the tools to detect. So, the next time someone tells you quantum computing is simply about building faster processors for existing kinds of problems, it is worth remembering what actually sits underneath the chip like Willow. This is not simply an engineering story about smaller transistors or clever new algorithms layered on top of familiar physics. It is a story about a machine whose entire method of operation seems to strain against the physical limits of the single observable universe, built by a team whose own lead scientist has publicly argued in writing that the most coherent explanation available involves borrowing computational power from realities beyond our own. A claim that remains genuinely contested rather than confirmed. Whether that particular claim eventually holds up under the weight of further evidence gets replaced by a more conventional explanation grounded entirely in standard quantum theory, or simply remains a genuinely unresolved question for decades to come. One thing is already completely certain. The line between cutting-edge engineering and the deepest open questions in fundamental physics has never been thinner than it is right now, sitting inside a chip that fits comfortably in the palm of your hand.